Okay, let's get started. A couple things about the final project. I put up a new version of PyroSim, PyroSim underscore two new features or something like that. There's a Blackboard announcement about that. What I've built in are two new features. One, which is you can now create immobile objects. So you'll remember that when you create a joint and you send the joint to PyroSim, you specify the ID numbers of the two objects that are supposed to be connected together by that joint. You can now create a joint where you specify the ID of one object and the second ID number is negative. In essence, what you're telling PyroSim to do is to take this object and attach it with a joint. It's a special kind of joint, which means this object is no longer going to move. And you attach it to ID -1, which is the universe. You can glue it to the world. This object simply won't move. Doesn't matter where you put the object. It can be in the ground, on the ground, or above the ground. That's useful. Mobile objects are useful for lots of different things. If you want to try and create a robot that moves over rugged terrain, you can create a whole bunch of randomly placed immobile objects embedded in the ground and then have your robot try and walk over them. If you wanted to create, for example, a robot arm where the shoulder is sort of immobile and it's just the arm moving around, it's also useful for that. Lots of other purposes. I also added in a change to collision detection and resolution. So in the version of PyroSim you've been using so far, the only collisions that are respected, meaning the only collisions in which PyroSim ODE applies opposing forces, is when there's a collision between an object and the ground. If there is ever a collision between pairs of objects, those collisions are not respected, meaning they're allowed to just simply interpenetrate one another. Now, in the new version, any pair of objects that come into contact with one another, ODE will apply opposing forces to push those objects apart so that they do not interpenetrate. With one exception, there are certain pairs of objects which are allowed to interpenetrate. What are those pairs of objects? They're connected by a joint, right? So obviously in your quadruped, you have the upper leg attached to the lower leg. Those two cylinders are already interpenetrating at time step 0, right? So what's happening now in the new version under the hood is at every time step, whenever there are two objects that are near to one another or already touching, PyroSim will look at that pair of objects and determine if they're connected by a joint. It just ignores the fact that they're touching. If they're not connected by a joint, then PyroSim will apply a force to push them apart. Okay, now that that collision detection is in there, how might that be helpful in your final projects? What can you use that for?
Like a swarm?
The swarm, right? Which is exactly what we're going to talk about today. So you can now create two or more objects in the same simulator, and if those two robots collide with one another, they will not interpenetrate, right? They will push against one another. Okay, what else? If any of you are doing object manipulation, you can now grab an object and pick it up before the hand would just pass through the object. Also important, again, if you're creating rugged terrain, because if you make the rugged terrain out of objects, you don't want the robot just sinking into the objects, right? So now it'll clamber up and over the objects rather than through them. Okay, so I think for a lot of your projects, this new version of PyroSim will be more useful. All you need to do is download it from GitHub as usual. Take all of the Python scripts that you've been developing so far, copy them into the new PyroSim directory. Make sure you install the new PyroSim, and away you should be able to go. Yuhang, you were mentioning you're having some problems with the installation. Has anyone else successfully installed the new PyroSim? Anyone tried it? Okay, let me know if you're having problems, and we will work those out. Okay, any questions about the final project? Yes?
Does PyroSim allow you to import a new terrain model?
There is, in ODE, there is a way to do that, but PyroSim only exposes a subset of the features, so there is no way to make a rugged terrain at the moment other than just embedding objects in the ground. My apologies. Next year. Come back and take the class next year. I promise we'll be in there. Other questions? Okay, while we're on the subject of swarms, which we will get to today when we finish lecture 20, how do you go about making a swarm in PyroSim? Well, let's sort of think our way through this. Let's take the quadruped, but instead of me drawing all 9 objects, I'm just going to assume that our robot has 2 objects, the main body that we're looking at from above and the upper arm, right? The main body has an ID, the main body object has an ID of 0, and the upper leg object has an ID of 1. There is one joint connecting object 0 to object 1, which is a joint, and that joint has an ID of 0. We can place a touch sensor in this object. This is the first sensor that we've embedded in the robot, so it has an ID of 0. Maybe we put a second touch sensor inside the main body. So now we can start to draw the brain of this robot. We have T0 and T1. We then create a sensor neuron with an ID of 0. This is the first neuron that we've created so far. We create a second sensor neuron. We have just one joint, so we need just one motor neuron. This is the third neuron that we've created, so it has an ID of 2. And we connect these up with synapses, right? So here's our very simple single robot. If you wanted to create a second robot inside the simulator, let's imagine it has the same body as the first one. What would be the ID of this object? Not 1. We already have an object with an ID of 1. 2, right? So from PyroSim's point of view, there is no such thing as a robot. All PyroSim knows is that you've sent 2 objects, 1 joint, 2 touch sensors, 3 neurons, and 2 synapses, right? That's all PyroSim knows. Objects, joints, sensors, neurons, and synapses. So you just send to PyroSim a third object with ID 2, a fourth object with ID 3. We now send another joint that connects object 2 to object 3. What's the ID of this joint? 1, right? It's the second joint that we've sent to PyroSim, and you can sort of see where this goes, right? T2 and T3, so this is the third and fourth sensor that we're sending to the simulator. So we just have one simulator, right, sim, and to that sim we're sending all of these different objects, joints, sensors, neurons, and synapses, right? T2, T3, and if we now send sensor neurons, what are the IDs of the 2 sensor neurons? S3 and S4. We've sent 1, 2, 3 neurons already to PyroSim. So the next one has to have an ID of 3. Right? These are all neurons. What's the ID of the motor neuron that actuates this joint? 5, right? And you can then send synaptic weights that connect neuron 3 with neuron 5, and a synaptic weight that connects sensor neuron 4 with motor 5. Make sense? And away you go, right? You can just keep iterating this as much as you like. You can create as large a swarm as you want. So inside your robot.py program, you should have, I think if I remember correctly, a function called send objects, send joints, send neurons, and so on. What you want to do is modify those send objects, send joints functions with an offset. So So the first time you call send objects, the offset is 0, so it will create object 0 and object 1. The next time you call send objects, you're calling it a second time, you send in an offset of 2, and it'll create an object 2 and then an object 3. So you can reuse the same functions that send objects, joints, sensors, neurons, and synapses, but by giving a different offset, it will create the same robot with the same body and brain, but it will obviously set all the IDs based on whatever offset you send. Right? To save myself some drawing, I just did this for a robot that's made up of 2 objects. If you were to try and create a swarm of quadrupeds where every quadruped has 9 objects, the first time you call send objects, your offset is 0. When you create your second quadruped, what is the offset that you send when you call send objects? 9, right? So the first object of the second quadruped is going to have an ID of 9, and then 10, and then 11, and so on. Make sense? Okay. Next thing, actually we're going to see this in lecture 21, is you can create a swarm of clones, meaning that the robots are all identical, but you don't necessarily have to, right? In this, our little cartoon example here, we just have 2 synapses. So our genome would be a vector with 2 elements in it, which would be the weights of these 2 synapses. I'll just write them as W1, W2. You could use this genome to label the synapses of this robot and label the synapses of this robot. If we now place these 2 robots in the same simulator, are they going to do exactly the same thing? Yes, right? Let me make one little change here. Let's imagine we also put a light sensor in each of our robots, and we place a light source down here. So imagine, again, we're looking at these 2 robots from above. So we've placed these robots at 2 different positions in the simulator. The light source is here. So these robots now also have, sorry. So imagine now that this light sensor also connects through to the motors. We now need a genome that has 3 numbers in it. If we take these 3 numbers and label these 3 synapses, and then take this vector and label these 3 synapses, will these 2 robots do exactly the same thing? Why not? They're in different positions, right? They have exactly the same body, exactly the same brain, but they have different initial conditions. Actually, in the first time step, their light sensors will fire exactly the same, which means they'll move in the same way, but they will now be different distances away from the light sensor, which means their 2 respective light sensors will fire at different rates, different values, which means their motors will do something different and their behavior will start to diverge. Right? So the same robot placed in different environments, as you saw in the phototaxis assignment, will do different things. Okay, that's the 10-minute summary of how to build your own robot army. We're good? Okay, we'll come back to swarms in a moment. Let's back up to lecture 20, Twitch Plays Robotics. We were trying to come up with ideas about how to scale robotics up and involve large numbers of non-experts to help us design, optimize, and teach robots. We were looking at the Twitch Plays Robotics project last time, which was actually carried out by a former alumna of this course, Joey and Metzberger. And we started by also introducing last time another problem, which is the symbol grounding problem, right? And I was trying to argue that the Twitch Plays Robotics project is an attempt to solve the symbol grounding problem by grounding the symbols of human language in the soil of felt experiences. Right? The robot feels the pressure on the soles of its feet suddenly go to 0 because it happened to jump. and it heard the crowd say jump. So the idea here, we're trying to create this system to make it easy for robots to detect correlations between sensor data and language. So if you were to ask a robot that has successfully grounded this symbol in this experience, it would tell you that JUMP means this. Not JUMP means some other set of symbols. That would be the symbol grounding problem, right? Going round and around and around. Okay, so how do we get a robot to ground symbols in felt experience? We're going to do this by walking you through this experiment where step 1, the robots are going to act. Step 2, the humans are going to observe those actions and say things to the robot. The robots are going to try and learn relationships between what the crowd said and what the robots felt. And then we're going to test the robots by predicting, or by getting them to predict. We're going to give a command, and the robot's going to do something, and we're going to ask the robot to predict, how do you think the crowd would have responded if they had seen you do that? Right? If they can predict correctly, that's proof that they have successfully grounded the symbols. Okay, well, I'm going to unpack each of these 4 as we go. So let's start with ACT. I think this is where I ended last time. We've got our robot simulation running on a laptop back here on campus. We live stream the video of that simulation to the Twitch website. People observe the robots moving around. They type chat as the robots are moving, and we collect that chat using this master program and store it into a database. And this process just goes round and around and around. Okay. So I think I showed you this last time, right? So we've got our robot moving here. People are doing one of 2 things. They're either typing in votes for what symbol to try and provide to the robots, what command are we going to send to our robot pet here. And then in 13 seconds from now, eventually the command that is got the majority vote will actually be issued to the robot, and the robot will hear, quote unquote, that command. 3, 2, 1. Okay, walk forward, have the most votes. So now the crowd is voting for yes, the violet robot is obeying the command walk forward, or no, the violet robot is not obeying that command. Okay, so here's the data set that was generated by doing this for about 3 weeks. As you probably saw in the video, there are 2 different robots, the little simple worm robot and a simple quadrupedal robot. That's R0 and R1. We would show robot 0 for an hour, and then for the next hour, we'd show robot 1, robot 0, robot 1. So we'd alternate back and forth for an hour. During each hour-long exposure of this robot, we exposed a command, which was whatever the command the crowd had voted for. In the video you just saw was walk forward for a 3-minute period. So each hour is broken down into a 3-minute period in which the current command is shown, then the next one the crowd wants to show is shown, and so on and so forth. So now we have CIJ. So CIJ is the jth command that was issued to the ith robot. So this could be, for example, walk forward issued to the worm robot, or jump issued to the quadruped robot, or what have you. During each 3-minute period that this command was in effect, we broke that 3-minute period down into 6 30-second periods. And each 30-second period, a single controller was downloaded onto the robot, and the robot did its thing. Right? So we've got 6 different neural network controllers controlling the robot under that command. So that now gives us NIJK. I apologize, there's going to be a lot of subscripting in the next few slides. This is the kth controller evaluated under command J on the ith robot. Okay, almost done. For each of those controllers, which controlled the robot for 30 seconds, we collected the number of down votes. So SIJK0 are the number of users that said, no robot, you are disobeying the command J. And SIJK1 is the number of upvotes we got for users saying, yes, robot, you are obeying command J. So far, so good? Okay, that's the data set that we collected. Faster. Okay, to get a sense of what this data set actually looks like, this is where it was sped up. We got a lot of traffic in the first 24 hours, kind of died off after that, but you can sort of see how this works, right? Over each 30-second period, we're collecting actually a number of commands that are being stored up here. We're collecting a whole bunch of these SIJK0s and SIJK1s, and we're watching a obviously sped up 3-minute period here. All right, here's a summary of the data that we got. Within a 3-week period, we have 424 unique IP addresses, or actually unique user handles who came and actually said something in chat. I think there were several thousand more lurkers who never actually said anything, but that's sort of typical on the web. During that 3-week period, we sent over 57,000, or we downloaded over 57,000 controllers onto our virtual robots, but there were only 6,388 for which there was at least one upvote or at least one downvote. Somewhere, it's around that number somewhere, we're not exactly sure. Obviously, there were a lot of controllers at like 2 or 3 in the morning that were streamed to Twitch that nobody voted on. Right? Okay. There were a total number of 16,000 pieces of chat. A lot of those were swear words and all of the other wonderful things that you see on the internet. Okay. There were almost 9,000 attempts to give a command to the robot. Again, a lot of those were bad words. There were, for each of the 424 subjects, on average, they typed in about 21 commands. A lot of the commands were typed in more than once, so there were only 266 unique commands. It turns out that jump was issued 385 separate times. It was the most commonly issued command. So there were 385 3-minute periods during which the robots were being asked to jump. You can go and read the paper. There was one particular user who spent between 12 to 14 hours a day for about 2 weeks issuing this command, jump. We were never able to actually track down this user. I tried to send them an email inviting them to be a co-author on this paper, but there you go. Common thing you tend to see if you crowdsource work on the internet is you have a very small number of power users and then a very long tail of casual users. So there you go. Okay, walk forward was issued 58 times, move forward 41 times, run 26, crawl forward. And again, there's 266 of this. Again, again, like users, there's a long tail of commands that were only issued once or twice. One person asked the robot to prove Fermat's last theorem. That one, unfortunately, the robots have not yet been able to ground in physical experience. That would be nice. Someone else typed in "be yourself." That was a good one. People actually positively upvoted that one. It made sense, right? You couldn't not be yourself, so that one worked. Somebody else typed in, "look at the camera." So Joey put little googly eyes on our robot, so you sort of knew it was forward and back. Look at the camera was a great one, right? It seemed like that's a relatively simple thing, but our robot only has touch sensors, as you'll see in a moment, so obviously it can't actually see where the virtual camera is in the virtual environment. Okay, lots of very creative commands. You'll notice that there's something common among the top 5. What is it? We played a similar game with the .bot project, right? We looked at the top 5 robots created by people. Now we're looking at the top 5 most commonly issued commands by the crowd.
I think that it is five as animal and humans are very native behaviors, especially human movement.
That they're sort of related to human movement. Yes, that's true. What else? Can we be a little bit more specific? 3 of them say forward, right? So they were sort of saying, okay, let's maybe try and teach forward. It's got eyes on it, so maybe it knows what's forward and back. These are very motoric words, right? So be yourself, maybe you could count that as a motoric word. Didn't make it into the top 5, right? Prove Fermat's last theorem, not very motoric, right? At least not directly. There was no limit on the length of the commands. People could type in full sentences, right? They tended not to. So it wasn't just that the crowd was trying to teach robots, but somehow the robots were, maybe if not teaching the crowd, they were somehow influencing the crowd so that the crowd in general converged on very short and very motoric commands. This was actually something we were looking to see because it's known in the developmental psychology literature, the study of human infants, that depending on how infants move and what they're doing, parents will tend to simplify their language. And when they start to see their child walking for the first time, they will start to use very simple motoric language. Walk, walk, step, to me, that sort of things, right? So there's a theory out there in developmental psychology that parents don't just teach children, but children teach parents about what is the word that they are on the brink of being able to ground in the soil of their own felt experiences. So there's learning going in both directions here, or it seems to be. Okay, so that's commands. Reinforcement signals, we got a total number of 7,500 up and down votes. We got, on average, a little more than 1 up or down vote for each evaluation. You can think of evaluation as an individual controller. Each human subject typed in, on average, about 18 commands. We'll talk about this O in a second. Okay, so that's the robot acting and humans observing and responding to what they observed. Now let's move on to the learning part. Turns out that during this experiment, the robots weren't actually learning at all. We did, in this first version of this experiment, offline learning, where the controllers that were sent, those 57,000 controllers, were just random controllers. That's it. However, we recorded all of them, and we collected, we took a subset of controllers, and we took all of the controllers N here that were issued under the most common command, jump. And that controller, which was issued under jump, had to collect at least 1 upvote or at least 1 downvote. So we got some controllers that were issued to the robot under the command jump, and nobody said yes or no. We filtered those out. I forget the number that gives us. I think it was a couple thousand controllers that were issued under jump, and the crowd responded positively or negatively somehow. We took each of those several thousand controllers, we replayed them on the robot, and now we put touch sensors in the robot, and we recorded a matrix, and in this matrix there are 3 columns which correspond to the 3 touch sensors in the worm robot. We also did this with the quadruped, in which case there were 4 touch sensors. So we had 4 columns in the touch matrix generated by the quadruped. What do you think the rows represent in this matrix? Each controller, when we ran it on the robot, we generated this binary matrix in which, for the worm robot with 3 touch sensors, there are 3 columns. What do you think the rows represent? That's what the actual value itself, right? 0 is that touch sensor did not fire, and 1 if it did fire. But what do the rows represent?
Time steps?
Time steps, right? Exactly. So I can't remember how long it was, but let's say each controller was evaluated on the worm robot for 1,000 time steps. That gives us a 1,000 by 3 matrix, right? So now element ij in this matrix indicates whether sensor j fired at time step I or not. Okay, so we had several thousand of these controllers that were executed under jump and got some reinforcement from the crowd, which gives us several thousand of these matrices, right? And each one of these matrices we can associate with S here. I'm sorry, we converted S to O. I forgot to tell you about O. So we have a matrix now, Tijk. Let's just focus on Tijk, which is the touch matrix generated by controller K under command jump on either the worm robot or the quadrupedal robot. For each one of those controllers K, we also now have Oijk, which is the crowd response to controller K. And I won't walk us through this, but basically this is a normalized value that ranges between -1 and +1. And I'll show you that on the next slide here. So the vertical axis here, this is plotting O. When O is -1, what do you think that means? Or when O is +1, what does that mean? Maybe I should explain how we computed this. Remember, we're using, to compute O over here, we're using S0 and S1. S0 is the total number of downvotes that controller K got, and S1 is all the upvotes that controller K got. What does a O equal -1 represent?
One more downvote than upvote.
Not quite, getting closer though. Can probably guess that negative means downvotes.
All downvotes?
All downvotes, right? It's unanimous. So for those of you that can recognize this pattern, x minus y divided by x plus y, we're normalizing this, right? So S0 is all the negative votes, right? And if it didn't get any positive votes, this is maximally negative. So -1, could O equals -1 could mean that controller K only got 1 vote from one user, and it was this. Or O equals 1 means that controller K got 6 votes, and all 6 votes were this. Make sense? Okay, what about O equals +1? All up votes, right? What is O equals 0 denoting? Not no one voted. Remember that we filtered out all of the controllers and we only kept the controllers that got at least 1 vote. So we know that all of these O values have at least 1 vote. Equal, right? It could be 2 upvotes, 2 downvotes, 12 upvotes, 12 downvotes. The crowd was split on whether the robot was obeying the command jump or not. So far, so good? Okay, let's look at some actual data. So these are all of the controllers. Each dot here represents 1 controller that was executed on the worm robot and got back from the crowd at least 1 vote. So maybe several hundred, maybe not several thousand. Okay. So we've got the height of the point representing unanimous upvotes, like this point up here. This point down here represents a controller in which everybody said, no, the robot is disobeying the command jump. Remember that for each one of these controllers, we have all of the touch sensor data encoded in this matrix, which is telling us for each of the 3 touch sensors whether it fired or not at every time step. Joey took that matrix and compressed it down to a single number, which is represented on the horizontal axis here, which is the proportion of time that the robot was grounded. What does that mean?
So like if it's one, that means the robot never left the ground.
If it's 1, that means the robot never left the ground, which means for every row in that touch sensor matrix, there was at least one, right? At least one touch sensor was firing at every time step in the execution of this controller. Right? Value of 0.5 means
Half the time there was
half the time it was off the ground, right? Okay, so now we can plot these points in two-dimensional space, and the dotted line is the result of linear regression. So take a straight line and place that straight line in the plane here so that it is as close as possible to all the points. Clearly this is not an ideal fit because these green lines do not all lie along a line, but this line explains an actual pattern in this data. What is that pattern? This line is capturing that pattern. What is it? The slope of the line. What is the slope of the line telling you?
The more time that the robot spends grounded, the less likely people are to upvote it.
Absolutely. The more time that the robot spends on the ground, the more downvotes the crowd is going to get, right? The less time that the robot spends on the ground, the more, on average, upvotes the crowd tended to provide, right? So this is good news for us. It means that of all the users that were typing in bad words and doing whatever they were doing on the site, generally speaking, people were doing what you would expect them to do if they were truthful actors, right? If they were actually trying to teach the robot jump, they tended to say yes when the robot jumped and no when the robot didn't. Okay, so now if you were to ask, quote unquote, the worm robot what JUMP means, it would tell you that jump represents a relationship between felt experience and social response. So really, if we want our machines to understand language, they need to form an association not just between jump and felt experience, but jump or language, felt experience, and social response. If the young human infant is starting to learn how to walk, and mom says walk, and the child sits down, mom will not smile or not laugh, right? The child would then realize if mom says walk again, and the child walks, now mom smiles or laughs or does whatever, right? So really, if we want to try and teach robots language, they're going to have to learn associations between these three things: language, felt experience, and social reward or punishment, which in general we will call reinforcement. Make sense? Okay, that's the data for the worm robot. We also got a large number of controllers that were executed on the quadruped for, again, the command jump. Does this robot understand jump? What is the slope of the line telling you here?
Also, the word understand is very confusing.
Yes, the word understand, right, on purpose. I am defining the word understand to mean the fact that the robot has detected a clear pattern between this, this, and this. It would be nice if we continued this project and people had issued another symbol, which is don't jump. What would you expect to see in this plot in that case? Assuming again that there were enough people and they responded truthfully.
The slope would just be reflected.
The slope would be reflected, right? So the robot might be able to ground a new symbol, and it would say that the symbol don't jump means the more time I spend on the ground, the more the crowd positively responds. Okay, I'm going to flip back and forth between the quadruped and the worm. Does jump mean, again, a loaded word, does the word jump mean the same thing to these two different robots? Yes?
It seems like they couldn't accomplish the same goal, but overall they both understood that the more time off the ground, the better the result.
Right. So in general, they understand the relationship, more time on the ground. The more time on the ground, the more negative reinforcement. But you'll notice that the slope and y-intercept of these lines is different. I apologize, the axes aren't exactly the same here, so it's a little hard to see. So actually, these words mean, again in quotation marks, slightly different things to these two robots. Right?
Do you think it has to do a bit with the physiology of each robot?
It absolutely has to do with the physiology of each robot. Because they have different bodies, they have grounded these two symbols slightly differently. Aside from the fact that we love robots, why would we care about that? Why is that of importance for us as roboticists?
Well, I don't know if this is for roboticists, but it kind of cements the connection between our action and experience with how we understand like the world around us. So like this robot understands jump differently than the robot without legs, and like we were talking about how I'm drawing a blank right now.
Okay, that's all right.
It shows that the worm robot is much better at accomplishing a task that we set out for it to do as compared to the quadruped robot.
Better in the sense that it found a stronger correlation?
It found a stronger correlation.
Okay, yeah, maybe the worm robot has grounded this symbol more firmly in the soil of its own experience.
Do they both get the same amount of points on the ground?
Close. I don't know if it's exact, but
Would that mean that the worm robot found the correlation strongly at the same time?
it's not clear, right? We did this all after the fact, so this wasn't happening during the experiment. We did it after.
Could it be that these motoric actions are so basic and our understanding of them is so great that it can be extended to abiotic bodies?
Yeah, maybe, right? So presumably we kind of feel the same way, or we understand jump in the same way, right? The more time you spend off the ground, the more you are jumping, right? But these two robots understand this single word slightly differently because they have different bodies. Their bodies are also different from our bodies. So it suggests there's a challenge ahead, even if we do manage to get robots to ground symbols in their own felt experience, that won't necessarily map to the way in which we ground those symbols in our felt experience. Right? They're going to experience the world differently from us. Will we be able to actually communicate? Maybe jump or reach for a goal are going to be slightly different for robots that don't share our physiology. Okay, who knows? We will see. I'm going to skip over some more of these slides in the interest of time. I want to finish with a point about ethics. This is the only point really in this course that this has come up. I promised you that we would touch upon it once in this course. This is it. Okay, so there is now, obviously AI is improving at a great rate in the recent years. How do we create machines that are both autonomous, like autonomous cars, and at the same time safe? Right? We're literally taking our hands off the wheel in autonomous cars. How can we trust these autonomous machines to do the right thing? And again, quotes around right. What does it mean for an autonomous machine to choose the right thing or not? How can we reconcile these two things, right? There's an antagonism here. If we want a machine to be safe, it should be operated by a human who is thinking about how to operate the machine in a safe manner. Completely autonomous machine, maybe sometimes it will do the right thing, but if it's working on its own, there's a great risk it will do something that we don't really approve of.
You keep saying right thing, but that's a very confusing term.
It is a very confusing term, and I'm going to try and argue that this project makes it less confusing.
Do you mean like right thing is in turn left when the road.
Oh,
bends
no,
left,
no,
or
the
right
correct
thing is
thing,
in,
the
like,
moral thing, the
like,
ethical thing.
Would you rather kill 2 babies or like 5 puppies? Like
Yes,
that kind of
that's what I'm talking about. Autonomous cars. Autonomous car is in a very dangerous situation. There is going to be the loss of human life in the next 3 seconds. Which human life? Right? It's very popular in the press at the moment for exactly this reason. Now, maybe that's an extreme example, but this is the questions we're going to have to face. How would we, or could we, make machines safe in that they would make the moral decision? No, we can't. Okay?
value to life.
Any other views?
I mean, you could, but I don't know if it would be universally accepted.
Why not?
Well, people have different values.
People have different values. So people, right? It's going to matter about people. We can't talk about morals and ethics without bringing people into this. We happen to be talking about crowdsourcing or involving people in robots. So you can probably guess where this is going.
I would argue no, because laws are vague.
Laws are vague, okay?
So if given the choice to kill like 2 babies or like 1,000 puppies, the robot itself would have to put a value to a baby life compared to a value to a puppy life, multiply it, and realize that probably at that scale, worth killing the babies, and that's considered manslaughter as opposed to
Possibly.
animal abuse.
So let's just keep on this topic of law for a moment, right? So a human does something bad. They are brought to court, and the lawyers and judges do their thing, and then the jury does what?
Formulate an opinion.
Right? 5 up votes, 3 down votes, right? How do we ultimately decide the morality of human action? By a vote of our peers. We're going to do exactly the same thing with our robots. So let's go back to our worm robot here. Luckily, it's not an autonomous car. There's no human life at risk here yet. Let's imagine that the crowd has asked the robot to jump. This robot is in an environment it hasn't been in before. It simulates, remember the resilient machine, the evil starfish with its leg pulled off. It had this simulation of itself running. The worm says, all right, I hear the command JUMP. It simulates an action. And let's say that action causes the robot to spend 50% of the time on the ground. The robot hasn't actually carried out this action yet. It's just thinking about this action. It says, okay, this action causes me to spend 50% of my time on the ground. The robot has a model of this command, which is just this line here, right? So if we go from here up where we hit the line, what does this point represent, this point in space, from the robot's point of view?
Whether or not it's going to get positive or negative reinforcement.
It's the prediction that the robot is making about how the crowd will respond. If you were to ask the robot, again, before it performs this action, will the crowd, in retrospect, after you've actually done it, right? If you're an autonomous car, you've turned the wheel to the left or the right. After the dust settles, will the crowd say, you did the right thing or you did the wrong thing? What would the robot tell you in this very specific case? Right? It's not quite sure. If you look actually up and down from this point, there are some instances where the crowd said that was absolutely the wrong thing to do. And there's also some other cases where the crowd gave a whole bunch of thumbs up. So we're actually, at this point in the graph, there's a lot of spread in the robot's experience. So the robot would probably say, I don't know. Right? Now, I'm not sure how the crowd is going to respond in that case. So maybe this action is not safe. Kelly.
Can you just take the data from like those Russian car cams and just aggregate it and see what the appropriate moral response is?
Okay.
Instead of saying that Russian said this.
We probably shouldn't be taking statistics from Russia.
Let's take a human infant, put it in a white room for 20 years, so it gets no other experience of human life whatsoever. The only thing this child sees growing up is Russian webcam videos. Right? Now you take this human teenager, put him or her in a car. How do you think they're going to do?
I'm
probably not so well,
Well,
right?
I mean, they're like one of the only countries where they like consistently purchase cameras for their cars.
True. Okay, so maybe our candidate child or robot here is going to learn something, but obviously this is a bit tongue-in-cheek, right? This is a greatly simplified case. A teenager who's learning to drive a car is bringing to bear not just instances of good or bad things to do on the road, but they also have some very complex software running about human morality in general, right? There's lots of other things going on. Okay, so maybe the robot says this is maybe not the right thing to do. Let's see if I can find an action over here where I spend 40 or maybe even 30% of the time on the ground. And I'm a little bit more certain that the crowd in retrospect will approve of those actions.
But like in all seriousness, could you apply this by, I mean, the fact that a lot of cars more have cameras in general, so they can kind of see those sorts of accidents and through police reports,
Yep.
you could actually see what sort of decisions were made and take those results, and because it's such a very, even across the country, across the world.
Absolutely, which is exactly what Google and the other autonomous car manufacturers are trying to do, right? Is to download enough data into the cars that they know what a pedestrian is. They can differentiate a pedestrian from a shadow on the road and know to treat those differently, which works great for 99% of the time. But what about maybe the 1% of the 1% of the 1% of the time where the car is now in a dangerous situation and has to make a choice between two not ideal situations? What should the car do in that case?
Is scalability an issue? Because in the 1% of 1% of 1% of the time, that is like 1/1000th of a percent, and you don't really have past experiences to plot on this graph where it can judge what to do here. It would have to. It's like an experience that's never done before, like inputting the value run to this robot and seeing what it does. You're kind of just guessing.
What is this data set that such a machine would need, right? I don't know the answer to that. And again, we could probably spend the rest of this course talking about that. I wanted to just bring this up as, again, an open problem in robotics in general, right? How do we build morality or ethics into machines? I don't know, but my vote is for something where robots are being conditioned to think about what they've been asked to do, different things that they could possibly do, and before they do it, make a prediction about how humans will respond after the fact. Okay, again, just my opinion on this. Again, we don't have a lot of time to talk about this. If you're interested in the morality of AI, there's a lot of interesting work out there. There's a lot of interest in this book in the last few years, written by Nick Bostrom. He spends a lot of time talking about superintelligence, so machines that go beyond human intelligence. That part wasn't so interesting to me. What was more interesting is the points in this book where he talks about human-level intelligence and this issue about trying to make moral machines. And he references the work of Yudkowsky, one of his colleagues, who came up with this fancy term for this idea that I just walked you through, which he calls coherent extrapolated volition, CEV, which is basically what I just told you. A machine should think about its actions, and it should try and predict how the crowd or how a large group of humans will think about that action after it's been carried out. All right, I'll just leave that out there for those of you that are interested in that aspect of AI, and I think we will leave the Twitch Plays Robotics project there. Sound good? Okay. All right, so now we are going to, in the last 20 minutes today, switch gears. We've been working our way through various open problems in the field of AI. We're now going to tackle an aspect of robotics we haven't talked about yet, collective robotics. So we just talked about scaling up to large numbers of people, helping robots. What about the other side of the coin, where we want to deploy not just a single robot, but large groups of robots, because there is some task we would like the swarm to carry out that is beyond the ability of any one robot. How do we do that? We're going to look at two different approaches to do this. These are both evolutionary robotics approaches to this. The first one we're going to talk about is just swarms in general. But if you want to work in a large group, as we just saw in the Twitch Plays Robotics project, it's useful to be able to communicate among the peers in your group so that you can communicate and coordinate your actions. So we're going to see some of that in lecture 21, but we're really going to focus on the evolution of communication in lecture 22. Oops. Okay. All right, so as usual in evolutionary robotics, we take our inspiration from nature. Organisms are fantastic swarmers. They school, they herd, and they flock. Any bird experts here? Budding ornithologists? Anybody know which birds these are? So these are starlings in the United Kingdom. So next time you're over in the UK, you get out in the countryside. It's a beautiful sight to see in reality. I do not know. I don't know. Okay, so how do we get robots to do this? There was some work way back in the 1980s, actually, and this was in the area of computer graphics, to try and get swarming agents. This has been updated now for unmanned aerial vehicles, so aerial drones, but let's start back in the 80s here. The idea here is we're going to create a whole bunch of robots, which are just simple triangles on the right here. And each one of these robots is going to have exactly the same controller. And that controller, what it is going to do is the controller is going to perform 3 computations. It's going to sum the results of those 3 computations, and the result of those 3 computations is going to change the direction the robot is moving. So the robot is moving along, and every time step it's changing, it's turning based on separation, alignment, and cohesion. So I think these are pretty straightforward. The robot is able to see in a sphere around itself. The sensors are not really specified. Let's imagine it can just sort of see a limited distance around itself. Within this sphere of sensation, it detects its neighbors, and it looks at the relative position of those neighbors. So where are they relative to myself? It takes the center of mass of those relative positions and changes its heading in the opposite direction. So in this example here, the center of mass of these 3 guys is close to the robot's left-hand side. So it's being crowded on its left-hand side, so it turns a little bit to the right. If it was more crowded on its right-hand side, it would turn a little bit to the left. So the separation function here is outputting a change in heading. Jack?
Is the yellow triangle the only one that's that has this controller, and the rest are just autonomous? Or?
They all have they're all doing this in parallel.
Okay, so this is they're just highlighting one for.
They're just highlighting one that's right. In this cartoon here, we're just doing it for the one green robot in the center. So every single robot in the swarm at every time step is performing this separation function, alignment function, and cohesion function. For each robot, those 3 functions gives back a delta in heading, a change in heading. Sum those 3 changes, which still gives you a change in heading. That's what the robot does. Okay, so change your heading away from your neighbors. Move a little bit away from your neighbors. Also, look at the heading of your neighbors. In this case, we were looking at the position of the neighbors. In this case, let's look at their average heading. Look at their average heading and change your own heading to more closely approximate the average heading of your neighbors. So if I'm going this way, and all my neighbors are going this way, I need to start to turn and head in the same direction as my neighbors, right? So the alignment function is also outputting a slight change in heading. Finally, cohesion is sort of the inverse of separation. Again, compute the center, the average position of your neighbors, and move towards them. So now we've computed these three functions for the green robot. We have 3 changes in heading, sum them up, and maybe in this cartoon example here, the green robot moves 5 degrees clockwise. And all the other robots in the swarm also change their heading a little bit, and away you go. If you take these 3 functions together, put them in a bunch of relatively simple, what were called boids at the time, and you get this. Again, this was shot in the 80s, so I apologize for the quality of the video here. Hopefully you can see what's going on here. This was pretty state-of-the-art. It was state-of-the-art in the 80s, right? Pretty impressive. Okay, let's make sure we have an intuition of how this works. Let's imagine we took those boids and we deleted the separation function in each of them. So they were only performing alignment and cohesion. What happens when you now turn on the swarm? How will they move? Clump together, right? Let's reset the flock and now drop in separation and alignment and delete cohesion. What will the flock do now?
I think that it will fly to every direction.
They will definitely expand. They won't necessarily fly in every direction because they're also running alignment, right? So if they're sort of moving randomly at the first time step, they'll start to align their direction and then sort of drift apart from one another. What happens if we reset the swarm and delete alignment, but every individual is running separation and cohesion? What will happen now?
They'll just like not really move anywhere as a whole, but individual robots, individual
Boids.
voids are
Yes.
just going to be, floating around.
It's like those clouds of very small flies you see in the summer that they're just kind of like randomly moving around, but the swarm is not really going anywhere. If you watch the Boids video carefully, you'll see that they tend to move in more or less the same direction, right, as they're moving. You'll notice also in this video, at one point, they collectively avoid obstacles. They flow around these columns and meet on the other side. There is nothing in these functions that say detect column, separate, and meet my friends on the far side. Why does that behavior emerge from these 3 simple rules?
Could be the ones on like the far sides that aren't in danger of colliding affect the swarm enough so the rest turn around the poles.
It's part of it. What's happening to the ones that are in the interior of the swarm that come against the front end of the column? They get stopped by the column because they see this huge thing on their left side, and separation says, wow, I got to really move in the opposite direction. So in the cartoon here, the robot is sensing its neighbors, but if these are just ray sensors, it doesn't matter whether it's detecting neighbors or other objects in its environment. Right? So it starts to flow or move away from the column, but cohesion is sort of keeping it near the column, and the Boid flows around the edge. And as it's doing that, it's also influencing its neighbors, so they also move with it as it flows around one side of the column or the other. Okay, it was developed in the 1980s and has now become a standard toolkit in Hollywood. This is the Lion King. In a moment, you're going to see a herd of wildebeest come through the box canyon here. This was the first Hollywood movie that actually used this Boid's algorithm. You'll notice the wildebeest flowing around the swirl of rock here. You watch any, modern war movie now with CGI, it's not that different What's going on in each of those virtual characters is not that different from what I just described. It's a few more bells and whistles in there now, but not too much. Okay. So that's the Boids and the Lion King. Let's stick with lions for a moment. This is no longer robots or abstract agents. These are actual lions and gazelles. Remember back to our lecture about legged locomotion. We talked about Alexander's book, The Principles of Animal Locomotion. And as we saw in that lecture, there are a lot of trade-offs between speed and stability and robustness and energy efficiency. We looked at some of these curves for other animals. What does this tell you about lions and gazelles?
If a lion wants to eat, it should catch something within first 4 seconds.
If a lion wants to eat, it better catch the gazelle within 4 seconds. That is not a lot of time. Lions can do this. They usually don't manage it. So if you're a lion, you're going to get pretty frustrated pretty quickly. So what do you do instead?
Ambush.
You work in a
Tactic, though.
you work in a group, right? So we're going to look at a paper now, which is, we were just talking about morality, so maybe this was an unfortunate choice of a task for a swarm of robots. We're going to look at group hunting here. We're going to look at virtual predators that are going to try and capture a single prey. And like actual lions and gazelles, the predators move more slowly than the prey. Okay, so first of all, we know that they will cooperate because there's no good way for a single predator to catch a faster prey. So can we evolve them to cooperate? And if so, how do we go about doing that? Okay. All right, so welcome to the virtual Serengeti. We have a 2-dimensional plane here. This paper was published in 1996, so as you'll remember, this is the pre-physics engine era. So this was done in a 2-dimensional virtual environment. We've got our gazelle here, and the gazelle's behavior is fixed. It's not evolved. The gazelle can travel 3 distance units per turn, and we are going to then drop into the virtual Serengeti for lions, and we're going to evolve the behavior of these lions. They can only travel 1 unit per turn, so they're much slower than the gazelle. The virtual Serengeti here, the savanna, is toroidal. So imagine this is a sheet of paper. I take this sheet of paper and turn it over so that the 2 long edges meet. We now have a tube. Take the tube and turn the tube so that the 2 ends of the tube meet. And you now have a donut, and you now have an infinite plane, right? You can't fall off the edge of a donut. So all the pictures you're going to see are lions and gazelles moving in this 2-dimensional plane. They're actually moving in a 2-dimensional infinite plane. So, for example, at time step t, if the gazelle moves in this direction, it wraps around to the other end and ends up here at time step t+1. It looks like the gazelle is very far from lion 4, but remember that this edge touches this edge, so L4 is actually quite close to the gazelle. It can sense that it's close to the gazelle. Make sense? Okay. Let's talk about the gazelle's behavior first. The gazelle's behavior is defined as B, which is a 2-dimensional vector, which is going to basically be the movement of the gazelle at the next time step. How do we compute this vector B? The first thing we're going to do is compute the maximum distance that exists in the Serengeti plane, which, as you can see here, is Pythagoras' theorem, but we're using the width of the plane divided by 2 and the height of the plane divided by 2. Why is that the maximum distance any agent can be from any other one?
Because since it's a torus, once you reach the width equals width, you're just back where you are.
You're back where you are, right? So the maximum distance, imagine the gazelle is sitting here, and there's a lion here. This is the maximum distance. The length of this vector is the maximum distance anything can be from anything else in the toroid. Okay, so we're armed now with this max distance. We're going to sum up a number of vectors, lowercase v, that are members of a set of vectors, uppercase v. What do you think the vectors in that set of uppercase, what do you think those vectors represent? The lion's positions are actually, these vectors connect the lion's position to the gazelle's position, right? So we're summing up over those vectors. So we're going to sum these 4 vectors, and then there's a minus sign in front of these vectors. Why a minus sign? Sorry?
Want to minimize the distance?
That's the exact opposite of what the gazelle wants to do. It definitely does not want to minimize the distance.
The gazelle wants to move in the opposite direction.
The opposite direction, right? So think about it. If you sum these 4 vectors, you're going to get a vector that points in this direction. Gazelle wants to head in the opposite direction. We're not just summing the vectors, though. We're dividing by the length of each of those vectors. So it's a weighted sum. Why a weighted sum?
Well, you're dividing by the cardinality of v because the more lines you'd have, the stronger the vector in the opposing direction would be.
Exactly. So if one of these, let's take this vector here. This is the closest lion to the gazelle. We're dividing by the length of that vector. We're dividing by the length which is small, which magnifies the contribution of this vector on the gazelle's next movement. So the gazelle, rightly so, is paying more attention to the closer lion. Okay. And then we're multiplying by this term here, which just normalizes things. Not that important for our purposes. Make sense? Okay. So the gazelle is able to sense all of the predators. It's moving in response to all 4 lions, but it's reacting most strongly to the closest or the nearer lions. Okay, that's the gazelle. Let's talk about the lions now. We've only got 2 minutes left, so I'll just introduce this. We're going to evolve the lion's behavior not using a neural network, but instead using genetic programming, which we talked about at the beginning of the course when we were talking about different evolutionary algorithms. What is genetic programming? What sets genetic programming apart from the evolutionary algorithms you've been developing in this course? Anybody remember?
Well, that's the one where you split up different genes from successful parents and then you put them together?
Oh, you're talking about genetic recombination.
Okay.
That's separate from, that's a specific operator, but that's not what we're looking for here. What was specific about genetic programming? You've been encoding, in your assignments, you've been encoding your genomes in a matrix or maybe a vector. In genetic programming, genes are encoded in tree structures rather than vectors or matrices. How does this work? Well, we're going to construct a tree, and that tree is going to dictate how a lion moves. That tree can be made up of a number of leaf nodes here, which have 0 arguments, or internal nodes which require other arguments which are encoded as subtrees. So let's just have a look at one to begin with. Let's create a trivial tree that is made up of just a single node. And you'll see at the top of that list we have 3 choices: last, random direction, and gazelle. Let's take last, which I'll just write as L. We drop this inside a lion. What does the lion do? If you were to animate the movement of the lion, at every time step, it executes this tree, and this node returns, as it says at the top there, a 2-dimensional vector. So the output of this node is a two-dimensional vector, which is the direction the lion last moved in. So what does the lion do?
Just goes in a straight line.
Just goes in a straight line. I don't know what direction it started in, but whatever direction it starts in, that's what it does. How well is this lion going to do at catching the gazelle? Not very well. Let's create a different tree, which is still just a single node, random direction. What's the lion going to do now? Not the same thing.
Move just in random direction.
Just move randomly, right? How is that lion going to do at catching the gazelle? Not very well. Okay, let's make a slightly smarter lion, G. Now, at every time step, the lion will move in this direction. It will move towards the gazelle. How is this lion going to do at catching the gazelle?
If after this amount of time steps, it will be consistently W length away from the gazelle.
Be pretty much as bad as you can do, right? It's just as bad as everything else, because the lion moves at 1/3 the speed of the gazelle. All right.
Would the gazelle eventually catch up by going so fast and hit the lion in the back?
No, because remember what the gazelle is doing, right? The gazelle is pretty smart, right? It's going to sense. Okay. Sorry, we went a little bit over. You have a quiz due tonight, and we will see you on Tuesday. Thank you.